this next session, we have two speakers. The first one is Jan Obloj, second will be Julien Guyon. And the first speaker is Jan Obloj from Oxford. Everybody knows Jan, so not much need to introduce him. And he will talk to us today about joint modeling and calibration of SPX and VIX via semi-martingale optimal transport. The floor, or rather the screen, is yours, Jan.
Thank you, Martin. And it's a great pleasure to be here. I know we would all rather be in Rio in person, but I think that's a good second best. I'm really very grateful to the organizers for their energy and enthusiasm that made us all come virtually together. I think that's really a great testament to the energy behind this series of meetings. So many thanks to Jorge and also to Marco and Bruno. I'm talking about joint work with Ivan, Gregor, and Leo. This talk came about when I was on my sabbatical in Australia. So it's also a great opportunity to thank for hospitality of their Center of Quantitative Finance Investment Strategies at Monash, but also of the Sydney Mathematical Research Institute, where I was the visiting fellow. I had a great time there. It was sort of just pre-COVID, so life was completely different, and I already missed those times dearly. But there was some really nice math finance coming out of this. So today is about joint calibration of SPX and VIX options. And the way we approached this problem was from an angle that came from robust finance and our related work on optimal transport. So I'm calling this semi-martingale optimal transport. But for the purposes of this meeting, you could really think of this as the sort of joint calibration in the spirit of Marco's work with co-authors back from 1997. And I'll later come back to this spirit. Okay, so I think it really fits well with the theme of the meeting, if you want. Here's the plan of the talk, and I'll really be quite brief. Some slides I'll just show you, for a couple of seconds. The purpose of this being that people who are then watching this on YouTube can pause and actually read in detail those definitions, while I'll be covering those at some speed for those of us who are participating in this live. Okay, but I want to cover very briefly basics of optimal transport to motivate how we come to this, and then cast the problem of joint calibration from the optimal transport perspective, but then dualizing and getting into the actual problem we're solving, and then presenting you numerics. And this is about SPX and VIX options, both instruments, so options on the S&P 500 index, as well as the options on the VIX futures. They very much relate to the volatility of the markets, or the market way of capturing that volatility. So there's very good arguments made, and Julien, who's following with his talk, will no doubt re-articulate that in order to account for the fact that you have liquid instruments in those options, you should be calibrated jointly to those instruments, and that not an easy task, especially for short maturities. Okay, and there've been a number of works in this. And I'm not going to, unfortunately, be able to discuss those today because of the lack of time, but somehow both in continuous time framework and in continuous time with jumps, there's a number of previous works that attempted to tackle this difficult problem of joint calibration. And more recently, Julien used techniques from sort of discrete optimal transport. And today what I want to present is a solution which is motivated by optimal transport, but which presents a sort of fully non-parametric calibration method for fitting a stochastic volatility type of model to options on SPX and VIX. Okay, and in some ways, that builds on the momentum, and hopefully the next talk will give you even more reasons to believe that those are nice tools to tackle those problems. I should mention there's some very, I think, interesting results coming from the rough volatility community, and when and if those are twinned with efficient calibration methods, those could also be very powerful tools. Okay, so this is my couple of slides on optimal transport. The original and sort of engineering, if you want, application of optimal transport is really thinking about transporting a particle X to a particle Y. And this is you can think of transporting something from mines to foundries or whatever. But this is really the idea is that you have some distribution of your initial assets, and then you want to transport this to the terminal distribution. And here, those are mu and nu. And you're doing this using a map T. Okay. So this is how Monge captured this problem. Now, for me, those states, initial and terminal, will be assets at time, say, T1 and T2. So I don't really think that assets move in deterministic maps. So I want to have some sort of more general version of decoupling, and that was done by Kontorovich. And in fact, mathematically speaking, this is a much more elegant or easier to solve problem. And here I'm optimizing now overall couplings. Okay, so all probability measures on the product space, such that the first marginal is mu and the second marginal is nu. And C again is my cost functional. C was the quantity that somehow captures the natural geometry of my space, if you want, the cost of moving something from X to Y. Now this problem comes with a very natural duality. Whenever you have a pair of functions phi and psi, which satisfy this inequality, if you integrate this against any pi here, you will clearly get on the left-hand side this quantity here, okay, and on the right-hand side you will get this quantity here. So you'll have this inequality, and now when you take inf over all pi's and sup over all psi's, you will actually get equality, subject to some nice conditions on your cost function C. So you can solve one or the other problem, and you can this way obtain this optimal transport problem. So if you now think about this and you try to be dynamic, this measure that jumped from mu to nu, well, it's somehow you can think of parameterizing this evolution, okay? And then in some intermediate time, say if this moves from 0 to 1, the intermediate time I have something that's in the middle between mu and nu, okay? And that's called McCann's interpolation. And if you transform, you can transform this original problem into this dynamic problem. And this was done by Benamou and Bernier in sort of fluid mechanics formulation. There's nothing stochastic here. You're really moving, okay? And you're trying to understand how to move this mass mu to mass nu. Okay? And you have some continuity equation which captures the fact that this should be some sort of nice movement of mass. And you have those initial conditions of mu and nu. And then you can rewrite, say, the initial, if my original cost functional C was square of the distance, I'll get some nice cost functional, but which now is along trajectories. Okay. And this is the continuous formulation. You could think that this is much more complicated because it's continuous as opposed to discrete. But in fact, this has nice numerics. Okay, so the original problem is quite hard. And this is paradoxically maybe easier to solve numerically. Building on this work, there were then ideas to move not along trajectories which are deterministic, but just like in the Kantorovich relaxation, I'm going to now move along stochastic trajectories. So I'm going to move along semi-martingales. Okay, and now we're really into sort of the core of the ideas, and this goes back to Mikami and Thielin controlling the drift, and then Tan and Tuzi controlling general the same martingale, and more recently papers that sort of emulate Benamou-Bernier in this stochastic setting for martingale optimal transport. The bottom line is that I have some problem V where I have cost functional along trajectories of my semi-martingale, and I want to minimize over all semi-martingales which have fixed initial and terminal distributions at time 1, 0, and 1. And now what I want to do is I want to apply duality to this problem. Okay, so I want to somehow dualize the constraints. So instead of the distributions and the same martingale, I'm going to somehow rewrite this. And the way to do this is that if you have some Markovian setting, you know that your distribution of your process satisfies Fokker-Planck equation. Okay? And you can write this PDE, hitting it with test functions. Okay, and this will give you the PDE for phi naught. And then your other part, which is the distribution, will be encoded here. So you can do this, and it has a nice dual formulation, which of course I do not have time to explain in detail here. But this you can really extend to quite a generic setup. Okay, so you could treat American options and many other things in this way. And more generally, you can really think of path-dependent constraints and path-dependent cost functionals. And this is what Ivan and Greg did in their first paper on this. Now, naturally, if you really want to do this, then path-dependent objects will induce path-dependent PDEs via functional Ito calculus. Right? So maybe solving this numerically will be more challenging, but somehow on a theoretical level, it really works very nicely. So let's go back now to my problem of options on SP 500 and VIX and see if how I can link this to this abstract same martingale problem. Okay? So I'm modeling under risk neutral measure my asset. This is S&P 500. Okay, and then what is VIX? VIX is the continuous time limit of your realized variance. Okay, so when you take the time sampling limit, you get some nice quantity here, and this is the key quantity I'm going to look at. So the integrated variance from T0 to T, and the VIX is actually the square root of expectation of this. Okay, so this is the key object. Most of you will know this object. If you don't, then well, just take this as a definition. This is an object which is of interest to us. So I want to model those together. Okay, and then I will have a certain number of instruments on those, and that's essentially call and puts options. So calls and puts on the SPX, the VIX future, which is just the expectation. So my today's evaluation of the price of VIX at some future date T0, from which I'm counting, and then at T0, this captures my T0 expectations of the volatility from T0 to T, which is usually sort of 30 days. And then I have calls and puts on this futures. And these are my calibration instruments. Okay? So I'm going to rewrite this to somehow fit this into the same martingale optimal transport framework. So I need to rewrite my assets. Okay? And my state now will be x1 and x2. x1 will be just log of my price process. So my price process was martingale. So now I get I take log, and Ito gives you this. Okay, so those are the dynamics of my x1, and x2 is this conditional expectation. So you can observe straight away that x2 at capital T has to be 0. Okay? And then this is the object which will feature in my VIX definition. So the object of interest will be x2 at time T0. And everything that I wrote before, okay, all those options are in fact expectations of some functions of my x, either x1 or x2, at some future dates. Okay, so this is the right hand side that I'm capturing here, and you don't have to worry about the exact formulae. The bottom line is that those are the type of constraints that you can handle through this optimal transport framework. So to give you an example, to which I'll come back later, if you just take a Heston model, okay, and then you rewrite this in the state space that I've introduced, you get x1, which was the log, and then you get x2. This is this conditional expectation. Okay? So it takes a moment to work it out, but you can work it out explicitly, and then you can work out the dynamics of that process, and this is given here. So there's some function nu and a, which are given here. Okay, well, they're explicit functions, so we can rewrite Heston in these new coordinates, and we'll use this later on. So what is our problem now? We want to calibrate to our market. So I have this initial distribution, which are just today's prices, and then I have certain functions gi, to which I'll come back, which depend now on my two-dimensional state process, and I want to calibrate. So I'd like to, these are my constraints, and now within all the models which calibrate, so these are these models here, I'm going to minimize some functional, and this will really just have the role of to regularize my process, okay, and allow me to have nice duality. So ideally, calibration is just finding a good element of this set of calibrated dynamics. Okay. So what are the dynamics? Can I understand this set a bit better? So I said x1 was the log price, okay, and x2 was this conditional expectation. So if you think about this as a two-dimensional process, you get some matrix. So alpha is the drift, and it's given here, and beta is the volatility matrix. And you see the sigma is an unknown process which was driving your S&P 500, your stock price, but everything else here and here will be prescribed in a moment, okay? Because what I see that those elements here, they will have to be equal to alpha 1 and alpha 2. these can be, these can be arbitrary. This element here has to be equal to sigma squared t. Okay, so I have some freedom in this part of my evolution because that's where the dependence between the VIX, the stochastic volatility character comes into play to understand the joint dynamics of my log price and my conditional expectation, which is driving VIX. Okay. Now, what is my my cost functional? This, as I said, was just supposed to be some sort of regularization tool. So what I'm going to do is I'm going to take some a priori model. This is my reference model. In ideal world, I believe that my this captures maybe some features of the dynamics, and I want to stay close to it. So I'm just going to take a cost functional, which is quadratic, okay, around this reference model, as long as I am calibrated, because if I'm not calibrated, then the cost should be infinity, which somehow throws away all those non-calibrated models. This is a slide for those who want to pause YouTube later on. For us, let's just summarize it very briefly. I have M SPX options, I have N VIX options. These are options which have some payoffs H composed with J, and J is the VIX future, okay, because they're options on the VIX future. And then I have this Xi. This Xi just captures the information which I wrote before, that X2 at capital T is equal to 0 almost surely. Okay? So the way I capture this is that I take some function which is 0 and 0 and otherwise grows very quickly, and I ask that its expectation is equal to 0. So this is my joint calibration problem. Now, the first observation that I'm going to make is that I can actually just consider stochastic volatility models. So at the moment, I had arbitrary processes. My sigma squared was just anything really adapted. And now I'm just going to look at Markovian projection. So this is this idea going back to Gyöngy and then Brunig and Shreve and others to really just look, instead of just general drift and volatility, you look at the conditional expectation of your drift and volatility, and this gives you a nice Markovian process which has the same one-dimensional marginals when the one-dimensional is in time, because my process is two-dimensional. So I have the slices in t which are the same as my same-Martingale model. Okay? And Jensen's inequality will tell you that this is greater or equal than that whenever your processes have the same two-dimensional marginals. And of course, this is a smaller set, so the other inequality is trivial, and hence we get the equality here. Okay, so I'm now back to Markovian setting, which means I can describe the evolution of my process through a PDE. Okay. And once I have this, I need some convexity. Okay, so I have to do some change of variables. But once you have convexity, you can do Fencher. So what we do is you introduce Lagrange multipliers to capture your constraints. So the constraints are market prices and your Markovian evolution. So this will be your Fokker-Planck equation. Okay, and then you dualize this. So your market constraints will dualize here, and lambda will be the Lagrange multiplier which captures your calibration to the market, to prices of those instruments. And now the AJB equation is what captures your the dual constraints from your PD. Okay, and of course you had nice duality, convex duality, so you can recover the original process, the actual process which then drives the other prices of unknown instruments through the duality. So looking at the gradient of your convex conjugate to F. So now this gives you somehow an idea for how to do this numerically. Okay. You'll start with some lambda, and then you're going to improve. So you have to understand what is the gradient in lambda, and if you compute the gradient of this reward functional here for some lambda, and then for some phi which solves the AJB equation, okay, then you will see that there's nothing else but the difference between your market prices and the model proposed prices. So this is this difference here. Okay? And that's reasonably easy to compute. This is just the usual pricing PDE. And I have many options, but in fact, there's just one really inversion of linear operators. So that's quick. So the algorithm, if you want to solve the problem, to sum up, is the following. Okay, here is our dual formulation, and what we need to do is we need to solve the AJB. This gives us phi lambda, and then I do the gradient in lambda. I improve lambda by gradient descent, and I solve AJB again. Okay? And this is in fact very similar to what Avellaneda, Friedman, Holmes, and Samperi did in one-dimensional context of a local volatility model. And in their context, this was motivated by somehow minimizing a Kullback-Leibniz divergence, and that led them to some sort of quadratic cost. And here, okay, we can work with an arbitrary f, but in fact, we'll take a quadratic f in a moment. So to solve the AJB, again, don't have enough time to really go into details, but you somehow have to do a policy iteration. This is where the actually is the most time-consuming element of the algorithm. And then you have to do some scaling for all these constraints to have similar sensitivities. And then you have to do some smoothing. And this is somehow where it becomes really interesting, because this reference model was your a priori model, but then you're going to do something a little bit like a Bayesian. So you're going to maybe start with a little bit, a restricted set of constraints, and then find a calibrated model, and then use this as a new reference. And then on top of this, smooth it with some sort of moving average to have something that looks reasonably nice. And then you keep repeating this, adding more and more constraints. And this somehow allows you to build a model which in the end looks and behaves quite regularly. So I want to discuss two examples. I have 4 minutes, so about 2 minutes for each of those examples. So again, I'm going to be very brief. And the idea is really very simple. So the first one is we generate data from Heston. So I have some Heston dynamics. I'm going to generate data for that. And I have SPX options with 2 maturities. And I have a VIX future, which matures at shortly after my first SPX options, and then looks 30 days forward, so looks until the second maturity of my SPX options. Okay. And I'm going to take 2 reference measures. Of course, if I took the reference measure, which is equal to my generating model, then the whole algorithm would stop straight away, and I would find that I can minimize the cost with cost being 0. So what I'm doing here is I'm either taking a Heston reference, but with different parameters, or a constant reference. And what you see is that this is with the Heston reference. So in red, this line here, and this line here, those are the reference measures, so the model which is not calibrated. And you see that what it does, the algorithm very nicely finds a calibrated model which matches both the SPX skews at 2 maturities as well as the VIX skew at t equals 49 days. And if you look here, sort of these small deviations here are in the wings, you're no longer constraints, and your reference measure is pulling you towards those values. And if you had a constant reference, of course, then the initial miscalibration is much more stark. But again, the algorithm converges reasonably quickly. And if you look at the actual dynamics, okay, then one thing that we want to check is that the x2 satisfies this constraint, which we call singular constraint. So at time capital T, x2 is supposed to be 0, and you see that this is nicely satisfied in all this, both in our first generating model, so our derivation of dynamics was correct, as well as the 2 calibrated models, one with the Heston reference and one with the constant reference. So if I take market data, in fact, I'll see really the same type of behavior and equally nice fit. I have even more data here. So this comes from September 2020, and I'm looking at short-dated maturities. These are known to be the challenging cases. And I have 26 SPX call options with 2 different maturities. And I have VIX future maturing in 15 days, and then 9 VIX call options on that future. And I'm going to start with a Heston reference model. But as I explained, I'm going to be smoothing this as I go on. So in fact, I'm going to start the numerics with a subset of those options. I'm going to calibrate a model and then use that calibrated model as a new reference. And then I'm going to use all those options. Okay. And as you see, the calibration results are really nice. So you get essentially perfect fit for both the SPX at 2 different maturities and VIX. As you would hope. Which in particular shows you that the problem is feasible, and there is a stochastic volatility model calibrated to those options. And just to a sanity check, the x2 satisfies the constraint, which is pulled towards 0, and my x1, which the log price, has reasonably nice looking dynamics under my under my calibrated model. Okay, my time's up, so I'm going to stop here. What we did is we proposed a non-parametric way inspired by optimal transport, but then really dualized to obtain a continuous time stochastic volatility model, which jointly calibrates to options on S&P 500 and VIX futures. And somehow this can be improved in many ways. In particular, numerics can be improved. What we did was really just a MATLAB implementation. And maybe for me, equally or even more importantly, it can be extended, I think, to other types of options. So even American options. You can really think that there's a lot of scope for incorporating various path dependencies in the way that the optimal transport inspired, say, martingale duality works. So I'm going to stop here. Thank you so much, and happy birthday, Marco.
So thank you very much, Jan, for a very nice presentation. So we have time to look at some questions. So I'm looking at the chat at the moment. I don't see any questions immediately. Maybe something that struck me along the way. So, I mean, when you were reparametrizing into your X1 and X2, you said for these you use semi-martingale measures. But I mean, the X1 actually is coming from a traded asset. So how do you ensure that you still have absence of arbitrage when you choose your semi-martingale measures?
Yeah, so I actually, what I did is, I just wrote my, because it's a calibration exercise,
okay.
I really write everything under a risk neutral measure. So this will be my pricing measure. So as long as I have nice sigma squared under which everything is well defined, my process will be a local martingale.
Okay.
And I'll have absence of arbitrage.
Yeah, okay.
So there's not a problem. Yes, then when you actually use the Markovian projection, you want to ensure that things are suitably adapted, etc. But once you've passed through the Markovian setting, you're on a sort of safe grounds.
Okay.
Just things running using Fokker-Planck equations forward.
Okay, so I see one question from Martino Grasselli. So he asks, did you calibrate on mid prices or on some interpolation like SVI for the VIX options? What about the bid-ask spreads there?
So these were the actual prices so Greg is now in BNP Paribas, so that's where we got the data. This was cleaned to account for a little bit of interest rates and dividends that you might have, for short dated maturities, and these days that wasn't much, but there was some adjustment. There are two maturities that we had. Okay, so both the SPX maturities were after the VIX future. Okay? So they were so the VIX here would be in 15 days and covering 30 days, so until 45 days. Okay. And SPX was covering the same time. So the idea was
but I think the question was, did you calibrate on mid prices or on some interpolation, or what did you do about the bid-ask spread?
Yeah, so this was on mid prices, I believe.
Okay, mid prices. Okay. There's another question from Carole Bernard. Do you have constraints on the number of options, on the number of dates? And is it easy to verify feasibility ex ante or only ex post after finding a solution?
Good question. So no, it's only ex post. The algorithm should give you infinity, so be diverging, because essentially, so non-feasibility means there should be arbitrage somehow, somewhere, and the algorithm should be picking this up and should throw you an infinite price. But it's only ex post. And of course, there's some issues with so for example, I didn't mention this, but you also need to specify the initial value. Now S naught or X1 naught, which is just the log price, that's fine. Today's price. But the today's price for X2, well, it's the today's expectations of the realized volatility going forward. So that you have to try to read off the options, and of course that depends on the wings which are not available. So there is a little bit of tinkering actually, and the algorithm it becomes a parameter in the algorithm. So if things do not converge or converge badly, you don't necessarily you cannot yet imply that this is non-feasible. Otherwise, there are no immediate constraints on number of options or intermediate dates in theory. In practice, of course, it depends on the numeric. So here with this gives you 38 constraints. Okay, so because there's also this constraints on x2 being 0 at final maturity, that already on a sort of normal desktop becomes challenging if you don't split this in two. So to have a more stable thing, we had to split this into subset and then iterate the reference and calibrate again.
Okay, so there's a last question. I will take 1 minute from Julien because it's a question from the boss, so I cannot overlook that. So George is asking, in the case of Avellaneda et al. For real data, the results had some spikes which indicated possible issues with the existence of solutions to HJB solutions in the classical sense.
Yeah, so
do you get similar problems here?
Yes. So in the theoretical results that we show have existence of results in viscosity sense, okay, because there are delta Dirac terms in this in the boundary constraints for your HJB. So you cannot hope to prove that you have the nice classical solutions. And we also get spiky type of results, which is one of the reasons why I had this smoothing. Okay. So in fact, what we do is we iterate this reference measure, and when before iterating, we smooth out the spikes, and that enhances stability. But somehow, in theory, this algorithm should be independent of this. It can give you different optimizers depending on your reference measure, and we found that a way to get best ones is to do the smoothing. So paper has endless pages of plots of the calibrated vol surface. You can have a look at. But yeah, if you don't do anything, you get spiky results and things which are not very stable.
Okay, so thanks a lot then, Jan. And I think we have to stop here. There's a coffee break afterwards for more discussion.